In this video, we'll do an example of the one sample t-test. Let's talk about Cooley High again. So passing the state test required for graduation is necessary, and the average state score on the test is 75. So we want to see if Cooley High is different in performance than the state. So we took a sample of 25 students at Cooley High, and we found the sample mean was 81, the sample standard deviation is 15. We're assuming the test scores are normally distributed. That's usually true. Now for alpha equal 0.05, would you conclude that Cooley High students perform differently than the typical state student? We use a two-tailed test because before doing the test, we have no real view about whether Cooley High is superior or inferior to the rest of the state. So our null hypothesis is that the mean is 75 for the Cooley High students. The alternative, it's not equal to 75. So that's a two-tailed test. So down here, we put down basically the critical region for that. You take basically the absolute value of the sample mean minus mu zero, which is 75 here, compare it to t sub alpha over 2, the t.025, with in this case 24 degrees of freedom, times the sample standard deviation divided by the square root of the sample size. Now how do I get that t.025 with 24 degrees of freedom? I use that t dot inverse function we discussed in the last video. If you type in t dot inverse 0.025 with 24 degrees of freedom, you'll get minus 2.06. So basically, we got a sample mean of 81. So basically, we look at the absolute value of 81, absolute value because it's a two-tailed test, minus 75, that's 6. We say, is that greater than or equal to 2.06 times the sample standard deviation of 15 divided by the square root of the sample size 25. So basically, that's 15 divided by 5 is 3 times 2.06 is 6.18. 6 is not greater than or equal to 6.18. We don't have sufficient proof to reject the null hypothesis, so we'd accept the null hypothesis that the Cooley High students are basically the same in ability as the state. Now we could do a p-value there, okay, because that's always a preferred way to look at the test. So we have a two-tailed test. What's the p-value? I've extracted it from our table above here. We take twice the probability a t-random variable with n minus 1, in this case 24 degrees of freedom, is greater than or equal to the absolute value of the t-statistic from our sample. What is the t-statistic from our sample? It's basically the sample mean 81 minus the hypothesis mean of 75 divided by the sample standard deviation divided by the square root of the sample size, which is 25. So 15 divided by the square root of 25 is 15 divided by 5 is 3. 81 minus 75 is 6. 6 divided by 3 comes out to be 2. So the p-value would be twice the probability a t-random variable with 24 degrees of freedom is greater than or equal to 2. So how do we find the probability that a t-distribution with 24 degrees of freedom is greater than or equal to 2? Well, we can use the t.dis function. We have to do 1 minus like we did with the norm-dis function. So basically 1 minus t.dist, basically the value of 2 that we got from our sample, comma 24, comma true, is the probability a t-random variable is greater than or equal to 2, which we'll have to double because of the factor of 2 here. So we get 0.028. So then the p-value for this test would be 2 times 0.028, which is 0.056. Now this is consistent with our accepting the null hypothesis because the p-value is greater than alpha, or a level of significance, 0.056. So in other words, if the level of significance had been 0.06, we would have had enough proof to reject the null, but since the level of significance was 0.05, we don't have enough proof to reject the null hypothesis. Now in our next video, we'll talk about hypothesis testing involving population proportions.